All right, folks. Let me start off with a word of prayer. Gracious God and Heavenly Father, thank you for this way that we can be in touch with each other and continue our education. Please bless us. We have a lot to keep up on, both as teachers and students. So please give us diligence. Most of all, keep us safe, keep our families safe, keep our nation safe, keep our community safe. Help us to look to you and to trust you during this time of difficulty. In Jesus' name, amen. All right, so this is kind of a long section, and I'm not going to expect you to turn in anything until Thursday, and I'll have a new lesson on 8.4 on Thursday, and then we'll just wait till next week to do the quiz on 8.3 and 4. Okay? All right, so you may want to listen through this a couple of times, and again, you can fast forward to whatever section. So first we start off with several definitions. All right, so first, an arc is a curve that is a subset of a circle. So an arc is to a curve what a segment is to a line or to a ray, okay? It's part of it, and so therefore it's a subset of it. Arc measure is expressed as the measure of the central angle intercepting the arc, okay? Any complete circle has a degree measure of 360 degrees. So if you had an arc that was 360, that would obviously be the total circle. All right, semicircle. A semicircle is half of a circle, an arc measuring 180 degrees. So I'd like you to pause the video right now, and if you would, identify the semicircle that is on this circle. So you could call it arc WY, you could call it arc WXY, you could call it arc WZY, and those would be the two semicircles for circle V. How about a minor arc? A minor arc is an arc measuring less than 180 degrees. Its measure is equal to the measure of the central angle intercepting the arc. So a minor arc, it's sort of like an acute angle. Of course, an acute angle is less than 90 degrees. A minor arc is less than a semicircle, is less than 180 degrees. So again, pause the video and ask yourself if you can identify some minor arcs here. So we have minor arc WVX, or WX, excuse me, and we have minor arc XY. Okay, so it's got to be less than 180. So again, the semicircles, arc WY, would not be a minor arc. Whereas a major arc is an arc measuring more than 180 degrees. Its measure is equal to 360 degrees minus the measure of the minor arc with the same endpoints. So again, pause the video, see if you can identify a major arc here. So again, the major arc would be, let's call it arc XYW, right? Or you could call it major arc XZW or WZX, okay? And the measure of the arc would be 300 degrees, right? You take the measure of the minor arc that it intersects with and you subtract that from 360. That gives you the measure of the major arc, arc XYW, arc XZW, however we want to label this. Adjacent arcs are arcs of the same circle that have exactly one point in common. This leads us to the arc addition postulate. The measure of an arc formed by the union of two adjacent arcs is the sum of the measures of the two adjacent arcs. So This is the same thing as the angle addition postulate that goes all the way back to chapter 1, right? If you had two angles that had a common ray that joined them, then you could add those two angles together. You know, for instance, here, if we were looking at angle XVY and angle ZVY, we could add those together to get the measure of angle XVZ. Okay, so we're doing the same thing now, only instead of angles with V as the vertex, we're talking about arcs. So for instance, arc XY and arc YZ, you could add those together to get arc XZ. Okay? All right, here's an example. Find the measure of each arc if in circle V if the measure of arc YZ is 45 degrees and the measure of arc WVX is 60 degrees. So they want you to find the measure of ZWY, which hopefully you can recognize that as a major arc, right? Greater than 100 degrees. And the measure of YXW. So first of all, because ZWY is a major arc, you simply subtract the value of arc YZ from 360 degrees. YZ is 45, so that tells you that ZWY is 315 degrees. Now the measure of YXW is going to be 180 degrees. So what they're telling you here is all right, how about the measure of arc ZW? So we've already determined what WX is, WY is, YZ is. ZW is going to be a minor arc, and because of the arc addition postulate, you can simply subtract the value of those other arcs. In other words, WY is a semicircle, YZ is 45, so you subtract that. So YZ plus ZW equals YZW, which we know is a semicircle. So therefore, using the addition postulate, we can simply move YZ over to the other side. 180, the semicircle, minus 45, arc YZ, gives us a measure of 135 degrees. How about the measure of ZX? Again, if we know the measure of WX and the measure of WZ, we can simply add those together, subtract it from 360 to find ZX. So the measure of ZX is the measure of ZY plus the measure of YX, right? Angle addition postulate. So YX is 180 degrees minus WX, which gives us 120. ZX is going to be 45, the measure of YZ, plus 120 degrees, which is the measure of arc ZW and WX. That gives us 165 degrees. Now, as it states in the middle of page 361, let's not confuse arc measure and arc length. The length of an arc depends on both the arc's measure and the radius of the circle with which it is a subset. So What they're saying here is that arc BA and arc ED are going to have the same arc measure, but just by looking at this picture, you can see that the arc lengths are going to be different because you have a radius of 6 for ABC, circle C. And then you have a radius of 9, right? 6 plus 3. And so obviously you're going to have a larger arc length for arc ED. Okay, and they actually work this out for you. You can see that the length of arc AB is 2 pi because you only have a radius of 6, whereas the length of arc DE is 3 pi. This leads us to the theorem at the bottom of page 361. If an arc of a circle with radius r, and therefore circumference c, which equals 2 pi r, has a degree measure of theta, that's a Greek letter theta, the arc length L is given by length equals theta divided by 360, in other words, the arc measure, times the circumference, okay? So you're gonna have to know the radius in order to come up with the circumference, and this is how you're going to determine the arc length. And as you do the homework for this, you're often gonna be given two of these variables, and you're gonna have to find the third one. So for instance, they're gonna give you the length and the circumference, and you've got to find the theta. You've got to find the arc measure. Or they're going to give you the theta and the length, and you're going to have to find the circumference. So again, it's going to involve some fairly simple math, but you just need to realize that you've got three variables here in this equation. And so they may give you two and ask you to find the missing one. It's kind of like trying to find the missing leg of the right triangle that you've had a lot in this chapter. All right, so find the value of each variable. So here you're given the arc measure, which has to be 90 degrees, right? That's your theta. Then you're given the radius, so you can find the circumference, and therefore you have to find the arc length. Find the arc length. So here's my formula. I plug in the theta, 90 over 360 times 2 pi 10. That's my circumference. Therefore, it's 5 pi yards. And when I multiply that out, I get approximately 15.7. So notice here, they're rounding to the 10th. So you can either leave your answers as pi, or if you want to multiply the 22/7 or 3.14, just round it to the nearest 10th, please, because that's the way that your homework is set up. All right, here we're given the arc length, right? That's the orange. We're given the radius so that we can find the circumference, and we need to find the arc measure, which is theta. So we set the problem up, right? Length equals theta over 360 times the circumference. So we've got 5 pi, that's the length. We're trying to find theta, so we put that in there over 360. And then we've got 2 pi 15. So if we move the 2 pi 15, we divide both sides by that, we end up with 1/6 equals theta over 360. Therefore, we multiply both sides by 6, which gives us 6 theta, or no, I'm sorry, we cross multiply, right? We're cross multiplying here. 6 theta equals 360. We divide both sides by 6, and we get theta equals 60 degrees. Okay, now we are given the arc length, 4 feet. We are given the major arc, okay? So if the major arc is 330, then theta has to be what? 360 minus 330, so theta has to be 30. Now they want us to find the radius. So again, we find theta by subtracting the major arc from 360. Then we plug that in. 4 is our length. Our theta is 30. And we need to find the radius. So we reduce 30 over 160 to 1/6. Then we put it all together and we get r by itself. So again, we would go through our cross multiplying or whatever technique we're using to get to this point. 24 over pi is the radius. And if we work that all out, we get 7.6, again, rounding to the nearest tenth. All right, here we are with example 3 at the bottom of page 362. I'm not going to work through all of this with you. They're wanting you to find the perimeter of sector XUY and segment XY. And I just want to remind you from chapter 7 what a sector is. So the sector would be the entire shaded area there from the center of circle U out to points X and Y and the arc. And so to find the perimeter for this, you're going to use the two radii, right, UX and UY, and then you've got to find the length of XY, arc XY. And then the segment is everything from the chord created by XY, right, out to the circle or the arc. And so the segment is going to be smaller, and the perimeter is going to be smaller there because that chord is going to be shorter than the two radii are. And they show you how to solve that there. So the top one is the perimeter of the sector, P sector, and then the bottom one is P segment. Congruent arcs. Congruent arcs are arcs on congruent circles or the same circle that have the same measure. So again, if they're congruent arcs, that means they're what? Their radii are congruent, and therefore if the arcs are congruent, that means that the arc measures are going to be congruent and the arc lengths are going to be congruent. Okay? So we're on page 363. And that leads us to a theorem. And again, make sure that you pause and read through these theorems several times. Okay? In congruent circles, or the same circle, minor arcs are congruent if and only if the corresponding central angles are congruent. Minor arcs are congruent if and only if the corresponding central angles. So pause and repeat that a couple of times. First of all, what kind of a statement is this? Well, if and only if is a biconditional. So we could say this: minor arcs are congruent if the corresponding central angles are congruent, or we could say if the corresponding central angles are congruent, then the minor arcs are congruent. Okay? So it just means we can reverse this and they're both true. So in other words, if angle P is congruent with angle Q, then arc WX is congruent with arc UV, or again, and this is all dependent upon congruent circles, right? So that's your first given, that circle P and circle Q are congruent. Or we could flip that around. If arc V is UV, is congruent with arc WX, then angle Q and angle P have the same measure, are congruent. Okay? Our next theorem: chords of congruent circles, or the same circle, are congruent if and only if they intercept congruent arcs. So let's say, however we determined it, that we determined that arc UV was congruent with arc WX. Well, that would mean that the chord UV, and again, that's a segment, that's a straight segment, is going to be congruent to chord WX. All right. Conversely, right, if and only if, biconditional, if chord WX is congruent with chord UV, then arc WX is congruent with arc UV. So again, this is telling us that if the chords are congruent, the arcs are congruent. If the arcs are congruent, then the chords are congruent. And here we've got a flow chart proof on page 364 that proves one of these things. It proves it from the perspective of if the arcs are congruent, then, I'm sorry, if the chords are congruent, then the arcs are congruent. So again, the circles are congruent, therefore the radii are congruent, right? That's the top one in the middle. We are told that the chords are congruent, therefore the two triangles are congruent through side, 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 right? The two radii are two of the sides, and then the chords are the third side. Therefore, we can use CPCTC to say that these angles are congruent. And if those angles are congruent, the earlier theorem told us that in congruent circles, congruent central angles imply congruent intercepted arcs. So again, this is the proof. The other proof, congruent circles are congruent if they intercept congruent arcs, chords, is one of the exercises. I'm not sure if we're going to be doing that one together or not. All right, here is another theorem. In congruent circles, chords are congruent if and only if the corresponding central angles are congruent. So first we were doing it from the perspective of the congruent arcs, excuse me. Now we are doing it from the perspective of the congruent central angles. And again, this should make sense to you because if those central angles are congruent, then the arcs are congruent. If those arcs are congruent, the central angles are congruent, and therefore these chords are congruent as well. And again, the proof for this is in the homework if you want to look at it. And it would involve the same kind of thing where you're proving the triangles congruent, and therefore you're demonstrating that the arcs would be congruent. In congruent circles, two minor arcs are congruent if and only if the corresponding major arcs are congruent. So again, this is somewhat like your linear pair theorem going back with angles. You know how linear pairs are always supplementary, they always add up to 180 degrees. Well, arcs are always going to add up to 360 degrees. So if you've got congruent circles and the measures of the major arcs are the same, then therefore the minor arcs have to be the same because you're simply subtracting the major arcs from 360 and you're going to get the same answer. All right. All right. So here's what I would like you to do for your assignment. And again, I'm not expecting you to get this into me until Thursday. I'd like you to do 2 to 22 even. I would like you to do number 32 in the B section, which is a fairly simple, it's just a 3-step transitive argument or proof. And then I would like you to do the cumulative review 50 to 55. All right, please let me know if you're having any issues. We may try to do a short live class this week to discuss this, just to check in with you guys. So be looking out for an email with an address to a Zoom meeting. Okay? All right. Take care, everybody. Bye-bye.